Yo, what's up, guys? Welcome back to another video. And this is gonna be a little longer than usual because I wanted to get into like a lot more information since I'm procrastinating right now and I want to make like a video. We're gonna be talking about minimum, maxes, and what concavity is inside of this video. So this is very, very important in calculus, especially in calculus 1 nearing the end of the semester term. Essentially, let's say you had the graph of x squared. So usually most of y'all will know what x squared looks like, which is this. Essentially, you can look at the graph and you can say that the minimum is that x equals 0. And you can tell just by simply looking at the graph. However, what if we don't have the graph, or what if we have a function that we can't exactly graph? How can we find the minimum, the maximum, or whatever else is asking for? So first off, let's define some terms. A minimum just means when a function is at a low point. So essentially what that means is just the lowest point out of two segments. So this is what I mean. So let's say you had a graph that looked like this. Essentially, the minimum at this point, the minimum of this function would be this and this. These are called local minimums. They're called local because it's the lowest thing on both ends of the function. We see here that the minimum, let me just draw with another color. The minimum is right here, and another minimum is right here. So these are called local minimums. However, there's also another thing called an absolute minimum, which is what this is. It's essentially what the lowest point on the graph is, the absolutely lowest point. So we see here that both of these points are local minimums. However, there's only one absolute minimum, which is here. So let's say this is x equals 3. This is x equals 1. Let's say this is x equals 2. So now you might be wondering what a maximum is. A maximum is essentially where the graph is at its highest point. And obviously, just like local minimums, you can also have many local maximums. However, you can only have one max at all if there's any. And we can see here that this is the absolute maximum. You can also count this one if you really want to, because I kind of stopped drawing that. Well, not here, here. Just make that red again. So there, this would be a local maximum. Both of these will be local maximums. However, this would be the absolute maximum. And so you might be wondering, well, it's pretty easy to tell off a graph. And another way you can tell is when the slope is equal to 0, or when it says horizontal. The reason why I say that is because if you're catching on to a pattern, you can see that when we're talking about a minimum or a maximum, we see that the slope at those points, at those x equal points, specifically is 0. And so here's how we find it with calculus. So I already said that x squared, the lowest point would be x equals 0. But how can we find that? Well, first off, let's take the derivative. The prime of x squared is 2x. From here, what we have to do is set the derivative, or the slope, equal to 0. Because as I said before, you can see that at the maximum or at the minimum, the slope is 0 at those points. So now we do 2x is equal to 0. And then from here, we can just find x. So the x point that it would be at its lowest is x equals 0. And from here, if we want to find the absolute minimum, all we have to do is just plug the x back into y. So we just do, let's just say f of x is equal to x squared. We do x is f of 0 is equal to 0. So therefore, the absolute minimum of x squared is 0. And that's really all there is to it. Obviously, it gets a lot more complicated. And so let's do some more. So then let's take the function, x to the third. And then let's say that we, obviously we know the graph of it is gonna look something like this. It's gonna look something like that. Let's find some critical points, shall we? We have f of x is equal to x to the third. Let's find f prime. F prime is equal to 3x squared because of the power rule. Now let's set the equal. So it says here that x is equal to 0. However, there's another thing that we have to do in order to find if it's a local maximum or a local minimum. It's called a sign chart. Essentially, what you're doing in these charts is finding out whether that function was increasing or whether it was decreasing at that point. Since I said that it's a local minimum here, I said it because simply of the graph. We can see that it's a graph and we can see that x equals 0 is the absolute minimum. However, when you have functions that you can't exactly graph or you don't have a graphing calculator, you need to have this skill where you're able to distinguish whether it's increasing before the point, increasing after the point, or vice versa, decreasing before and after. So this is how we do it. First, we have the sign chart. And then from here, we plug in numbers before 0. So let's say -1. And then after 0. So essentially, what we have here is we're checking whether it's increasing or decreasing on -1 and 1. So how we do this is we just plug both of these numbers back into f prime. Since f prime is the slope at any point, what should go out is the slope at that point. So let's do f prime of -1. F prime of -1 is just 3, -1 squared, which is just equal to 3. Makes sense? Then f prime of 1, which is equal to 3 again. From here, what we can decide is that at -1, before 0, it's always increasing. And it's the same for after 0, it's always increasing again. Now, what this means is that there's no minimum or max at x equals 0. Now let me show you why. Let's take x squared. Let's take x squared again, right? And let's do everything else that we just did for x to the third. Let's do our sign chart again. -1 and 1. Now let's plug back in for 2x. F prime of -1 is equal to -2. F prime of 1 is equal to 2. So we see here that before 0, it's always decreasing. And after 0 is always increasing. If you follow the signs here, you can see that you're getting a minimum. Since it's decreasing, it reaches its lowest point, which is here, and then it continues increasing again. So you could see here how the arrows show whether it's a minimum or a maximum. However, for x to the third, since the critical number, or where the slope is equal to 0, since the critical number is not a minimum or a maximum, due to everything increasing, we can see that it doesn't have a minimum or a maximum at that point. And essentially, you could see that with the graph as well. You can see the slope increasing, and then it stops here for a little bit, and then it just continues increasing. That's essentially how we find the minimum or maximum. Since there is none, then we just say there's no minimum or maximum at x equals 0 for x to the third. That's what distinguishes these functions. we can see through calculus how we're able to find the minimum or maximum at a specific point. Now, let's say we had a domain restriction. So let's say we had a random function. F of x is equal to x to the third plus 2x plus 3. Right? And then we're restricted to the domain of 1 and 4. Let's find the maximum and the minimum. Shall we? So first off, what we have to do is we have to find the derivative first, or the slope. So f prime of x is equal to 3x squared plus 2. Now from here, we set everything equal to 0. That might be impossible. Never mind. Just make it negative. Minus x squared. So now we have f prime of x is equal to x to the third minus 2 for the derivative. From here, we set it equal to 0. Let's just make this x squared. So let's just make this x squared because I'm not trying to work with complicated numbers. I don't have a calculator on me. So let's just say that the original function was x squared minus 2x plus 3. F prime of x would be 2x minus 2. So we just said 0 is equal to 2x minus 2 in order to find the critical point at that value. So let's find it. 0 is equal to 2x minus 2. Let's solve for x. X is equal to 1. The important thing to notice with these functions is that it has to be between the domain in order to see what we're trying to find. If it's outside of the domain, if the x value is outside the domain, it does not matter what happens. It cannot be used. So the next method is going to be something called the candidate test. What it essentially is we're using the candidates and we're just plugging them back into the function in order to find the minimum or the maximum. So essentially what we can do here, what I like to do basically is just make like a little t-chart. So since we know one of our critical numbers is 1, but we know that 1 is already in the domain, so we don't have to, count for 1 twice. So we can just say that the numbers are 1 and 4. And from here, we just plug them back into f of x. So f of 1 is equal to 1 squared minus 2 times 1 plus 3. 1 squared is 1 minus 2 plus 3. 1 minus 2 is negative 1. Am I doing this right? 1 minus 2, I can't do simple arithmetic. 1 minus 2 is negative 1 plus 3 is 2. I hope so. F of 4 is equal to 4 squared minus 2 multiplied by 4 plus 3. 4 squared is 16 minus 8 plus 3 is equal to 11. So f of 1 is equal to 2 and f of 4 is equal to 13. Therefore, we know that f of 1 on this domain and of this function, this will be the absolute minimum and this will be the absolute max. Simply because their y values show that it's the minimum or it's the max. And that's essentially it. So let's say we had a function that gives us multiple critical points. So let's say we had the critical point. Actually, let's say we had the function f of x is equal to 1/3 x to the third minus x plus 1. And we're on the domain of 2 to 6. Why not, shall we? So first we have to find where the slope is 0. So we do f prime of x. We do power rule. We bring down the 3 minus 1, that's x squared, minus 1, and that's it. So now let's set it up equal to 0. From here, we can tell that the critical points are going to be x minus 1 and x plus 2. I'm sorry, x plus 1, since it's just a difference of squares. However, we can't use any of these values, and it just made it seem useless of why I didn't use these values. But we're restricted to this domain. Since the x coordinates are outside of the domain, we can't use those for our candidates test. So they're utterly useless to us. And this might seem not that intuitive at first. However, it makes sense when you're on a specific domain. So from here we make a little t-chart again. And now we just find what the values of f of 2 and f of 6 are in order to find our minimums. So we have f of 2, which is equal to 1/3, 2 to the cubed, minus 2 plus 1. 2 to the cube is 8/3. We can just simplify this to be -1. 8/3 minus 3/3 is equal to 5/3. So f of 2 is just 5/3. F of 6 is equal to 1/3, 6 cubed, which 6 cubed, 36 times 6, 216, 216/3 minus 6 plus 1. I'm not going to do the math, but this is obviously the maximum. And this is obviously the minimum. Now let's give another example. I'm trying to think. Let's say we had the function (1/3) x to the third minus 4x plus 5, and then we had to find it on the domain of 0 and 5. Let's do it, shall we? So first off, we have to find the slope. So f prime of x is equal to x squared minus 4. We set it equal to 0. We see that it's just a difference of squares again. And we see that 0, or x, is equal to plus or minus 2. However, since we're restricted to the domain of 0 to 5, we see that we can only use positive 2. And so this is where it gets a little different. Now we have 3 values that we have to worry about instead of just 2. Since we're measuring the endpoints, but we're also measuring the critical number that we found to be inside of the domain of f of x. So from here, we just set up our little t-chart again. 0, 2, and 5. And now we just find for all the values. So we do f of 0, which is equal to 5. F of 2, which is equal to 8/3 minus 8 plus 5. This simplifies to -3. 8/3 minus 9/3 is equal to -1/3. And then from here, we do f of 5, which is equal to 125/3 minus 20 plus 5, -15. 125/3 minus -15 times 3, because we're doing common denominator. 125 minus 45 is 80/3. So we get 8/3. Now, if you want to ask me what that value is, it's roughly around 26, 27 really, if you round it up. So now we know that on the graph of f of x, and on this domain specifically, we know that 27 is the absolute maximum, and that negative 1/3 is the absolute minimum. It's kind of cool to figure out what these y points are without even knowing what the graph looks like. F of 0 is kind of useless, but it's really not. But this is really, really cool to tell, simply because you know when the graph is increasing or decreasing at that point. And here's what I mean. Let's take the same function again. Let's take 1/3 x squared. I'm sorry, x to the third minus 4x plus 5. But let's just say that we had the whole domain. We're just going from negative infinity to infinity, right? Find f prime of x. So let's find the critical numbers. X is equal to positive plus or minus 2. So now let's see when in this graph specifically, all around the domain, when this is increasing or decreasing. So we set up our sign chart again. -2 and 2. From here, we find numbers in the middle. So we know when on these intervals, whether it's increasing or decreasing. From -2 to 2, we can do 0. From 2 to infinity, we can do 3. And then we can do -3. From here, what we can do is we can just plug these numbers back in, just the same as we did with the other functions a while back, in order to find what f prime of x is. So let's do f prime of -3. F prime of -3 is equal to -3 squared minus 4, which is equal to 9 minus 4, which is equal to 5. So therefore, since the slope is positive at this point, we know that from negative infinity to -2 is going to be increasing. And then let's do 0. F prime of 0 is equal to 0 squared minus 4, which is equal to -4. So at this interval, this is decreasing. Now let's do f prime of 3, which is 3 squared minus 4, which is equal to 5. So from here, we know that to infinity, from 2 to infinity and beyond, it's increasing. So what can we say about these intervals? So we can say that f of x is increasing on negative infinity to -2. And then we can do the union symbol in order to symbolize this. But you don't have to do that. You could also just do this. And then it connects it. But we know that the interval at which f of x is increasing is from negative infinity to -2. And from 2 to infinity. And we know that f of x is decreasing on -2 to 2. I don't know, like, isn't that kind of cool? Even without knowing what the actual graph looks like, or without using a graphing calculator, we know when these functions are going to increase or decrease. We know what's going to happen. We know exactly what's going to happen. And that's just what blows my mind, really. Because with calculus, you're able to do these things, and without even looking at the graph. Like, I'm guessing this is why they don't allow a graphing calculator on the AP test. So, without further ado, let's go into another topic. Let's talk about concavity. Oh, I don't like that. Let's make it like a little bit bigger. Let's talk about concavity. Concavity is essentially the second derivative of f. So let's say we take f of x equal to x squared again. There's two types of concavity, concave up and concave down. What concave up is essentially, which is the shape of the function. So it's essentially this shape. And you might be wondering, oh, it just looks like x squared. Well, chill out. I'm about to tell you. And when it's concave down, it's this. Now, guess what? There's so many cool things you can do with this because, like, I'm just so excited to tell you. But basically, with concavity, we can find what the shape of the function might look like, even without looking at the graph. Isn't that just crazy? So look, we have f of x, which is equal to x squared, right? We all know the graph. It just looks like this. But why is that? And that's such a bad graph. My drawing skills are terrible. But why is that? Well, since I said that concavity is equal to f double prime, or the second derivative of f of x, let's find why. So we have f prime of x, which is equal to 2x. But from here, since we said concavity is a second derivative, wouldn't it be smart to just find the critical number of f prime of x? So essentially what I'm telling you to do is find when f prime of x is equal to 0. And we know 2x is going to look like this. This is the derivative, right? Let's do it. F prime of 2, f double prime of 2x is equal to 2. This is always going to be a positive number. So your concavity for here is going to look like this. What does that tell us? Well, what that tells us is for all negative infinity to infinity, x squared is always going to be concave up, simply because f double prime of x is always going to be positive. Since it's a constant, it's always going to be positive. That's why it gives off the shape of this. And now there's something more interesting as well. Let's find concavity for x to the third. I already said there's no absolute or absolute max or absolute minimum for x to the third. But if you know the graph, you might realize that it changes shapes a lot. You might say that this is concave up, and that this might be concave down, because it looks like that. Let's prove it with calculus, shall we? F of x is equal to x to the third. F prime of x is equal to 3x squared. So then let's find f double prime of x, which is equal to 6x. Now from here, since we just set it up equal to 0, 0 is equal to 6x, so then therefore x is just equal to 0. So let's find if it's really concave down or concave up. Just like we did for the critical numbers for f of x, we also have to do the sign chart for f prime of x or f double prime of x. So since our critical point for f prime of x is x equals 0, we do the same thing, get our values in. Now we do f double prime of -1 is equal to -6. And then f double prime of 1 is equal to 6. So what that tells us is that from negative infinity to 0, f of x is concave down. And from 0 to infinity, f of x is concave up. Isn't that just so cool? Isn't that just so cool? I just proved why the shape of this is this. This is what you can do with calculus. Even though there might not be an absolute minimum or an absolute maximum, you can definitely prove as to why the shape looks like that in the first place. And so let's do some more, shall we? Let's say we had f of x is equal to x to the third minus 3x. For this one, let's find the absolute max, absolute min, and concavity. So from here, f of x is equal to x to the third minus 3x. For the absolute max or for the absolute minimum, what we can do is we can do f prime of x is equal to 3x squared minus 3. We set it equal to 0. 3 is equal to 3x squared. So therefore 1 is equal to x squared. So therefore it's plus or minus 1 equal to x. That's not the main, that's just the answers in parentheses. Anyone else with something else is cool? Since these are the critical points for f prime of x, doesn't that just mean we can plug it in for f double prime in order to find concavity? Here's what I mean. Let's just find the absolute max and absolute minimum first before we go into such ludicrousy. So first off, since we know our critical points are -1 and 1, let's do our little t-chart. And we'll find when it's increasing and decreasing too. So we have -1 and 1. F of -1 is equal to -1 cubed minus 3 times -1, which is -1 plus 3, which is equal to 2. Then we have f of 1, which is equal to 1 to the cube, which is just 1 minus 3, which is equal to -2. So therefore, we have our absolute max of 2 and our absolute min of -2. But now, with the sign chart, let's see if that's actually factual. We have -1 and 1. Plug in some values to see. F prime of -2 is equal to 3, -2 squared minus 3. -2 squared is just 4 times 3 is 12 minus 3 is 9. Since this whole thing is 9, it's increasing. F prime of 0, I'm sorry, is just equal to -3. So therefore, from -1 to 1 is decreasing. And now you might see a pattern. So the function is increasing from -infinity to -1, and from 1 to infinity, and decreasing from -1 to 1. And you know how I said that -1 is the absolute max and 1 is the absolute minimum? Well, even before we could have plugged in the values, we could have saw that through the sign chart that -1 is indeed the max due to the arrows. We see that it's increasing, reaches the point of 0 where the slope is 0 here, and then it continues decreasing until it reaches 1, which is the minimum, and then it increases from there. It's just like a mountain. Now, let me prove it through another way, and you won't believe this. You can prove it using the second derivative, and here's what I mean. Our critical points are -1 and 1. F double prime of x is equal to 6x. Now let's plug these values in. F double prime of -1 equal to -6. And then f double prime of 1 is equal to 6. Now you might be wondering, well, I have no idea what this means. I literally have no idea what this means. Well, if you recall, the values at which it would be negative would be concave down, and the values of which f double prime would be positive would be concave up. However, you can see that when concavity at these points is negative or positive, you can see that through the actual signage of which it is, that you can see that this is a max and that this is a minimum. Since the slope here is 0 and the slope here is 0. This is why it's so cool. This is literally why it's so cool. And let me prove it to you again. So, f double prime of x is equal to 6x, right? As we said before. So now let's do our sign chart. 0 is equal to 6x, x is equal to 0. Plug some values in. F double prime of -1 is equal to -6, and f double prime of 1, we already did this, is equal to 6. So we can see that from -infinity to 0 is concave down, and from 0 to infinity is concave up. When a value switches concavity, I think I should have said that, it's called an inflection point. Let me just write this here. An inflection point is when, at the point, it switches concavity. So our only inflection point would be 0, but you have to be careful because you might get some more critical numbers in terms of f double prime, and they may not be inflections. This is why you always check with the sign chart. However, an inflection point is when the x coordinate at that point is switches concavity. But you can see why through the second derivative you're able to find the absolute maximum or the absolute minimum. Isn't that just so cool? Even without knowing what the shape of this graph looks like, we found out essentially what the shape of the graph looks like. The maximum, the minimum, when it's increasing, when it's decreasing. This has probably been my favorite video, and if you stuck around for this long, thank you for watching. It's really difficult explaining this subject since I'm just studying for finals right now. I got my final, I don't know when you're watching this, but I got my final this Friday. And essentially, this is what's going to be on my final for math. But hopefully you liked when I explained it and how hopefully you understood. If not, I can always go deeper into this topic. However, this has been minimums, maximums, and concavity. Thank you for watching. If you stuck around for this long, again, thank you. Thank you for watching. I'll see you on the next one, and goodbye.